This is part 3 of photoelectric effect, and in this section I will discuss about the history, that is the part 3 in this series. In the first section we have discussed about the basic definition of electron emission and the work function. Then we define the basic terminology and definition of electron volt. Then after some numerical values of the metals for the work functions and the way by which one can determine that the photoelectrons, the physical process. And now in this section I am discussing about some historical part of the photoelectric effect, in which the first name comes about the Hertz. So what was the Hertz observation in the photoelectric effect? As you know that the photoelectric effect phenomena is the emission of electron. What is it? It is emission of electrons, and electrons are negatively charged particle. These are negatively charged particles. So what is the idea of Hertz experiments? When it came, basically photoelectric effect phenomena, it was discovered by Henry Hertz in 1887 when he was experimenting on electromagnetic waves. Right, electromagnetic waves, for an example, light waves are an electromagnetic waves. Electromagnetic waves are those waves in which electric field and magnetic fields are perpendicular to each other. If suppose electric field along this direction, magnetic field will be perpendicular to that. This is magnetic field, and also to the direction of propagation. If this is the direction of propagation, right, that you can define by the wave vector k. So this is the electric field along this direction, and this is the magnetic field along this direction, and wave is propagating along this direction. You can say this is y, this is x, and this is z. Right. So this is one of the important properties for the electromagnetic wave. So it basically, this effect came into observation of the Hertz when he was experimenting on it. So here some points which you have to remember when you study the photoelectric effect. Number 1, when light shining on the metal surface, here you have to specify the light, the radiation, what is the source of that, and what type of materials you have chosen. But the point is, when light shining on the metal surfaces, free charge particles known as electron escape from the surfaces. But the point is, electrons near the surface absorb enough energy. Right, if suppose this is a surface and these electrons escape from the surface, when it will happen and how it basically this process will take place, and why. So all these answers are discussed below. You can see here Electrons near the surface absorb enough energy from the incident light. You fall some light on the surfaces, that is a radiation of particular frequency, and when the electron absorbs enough energy, right, so then what happens, it absorbs the energy from the incident radiation. Why? To overcome the attractive potential or force, or in other words energy, that is in between the free electrons and the positive ions of the material. In the earlier section I have discussed and show that the inside the material there are positive electrons of the material and the free electrons. These electrons cannot escape the surface because of the attractive force in between the ion and this electron. So when the electron absorb enough energy to overcome this force or the potential which is attractive in between these two, then this electron can comes out from the surface, and this is the emission of the electron. Here two more scientists, Hertz and Lenard, also investigated the photoelectric emission phenomena in detail during 1886 to 1902. Right, so some conclusion are discussed here, and these points are: number one, when ultraviolet radiation were allowed to fall on the cathode plate in a vacuum glass tube, right, there are two cathodes, one is anode, two electrodes, one is cathode and second is the anode. So here light is falling on the cathode, and where it is kept, this cathode plate is kept into the vacuum glass plate. So what has been observed? It has been observed that a current flows into the circuit. And second point, if this radiation stopped to fall on the surfaces on the emitter, right, that is the cathode plate, this current also stops. So here you can see this is the cathode plate, this one is connected to the negative terminal of the battery, and this is the anode plate connected to the positive terminal of the battery. So when a particular frequency of light fall on the surfaces of the cathode plate, electron basically absorb the enough energy to overcome the attractive force and escape from here. These particles are actually electrons, and here you see this is the positively charged plate. At high potential, this positive charge plate will attract these electrons, right. So all these electrons are moving towards the anode plate. This is the second point. So these electrons which emits from the cathode are known as photoelectrons, or the process by which electron emits from the cathode surfaces are known as photoelectrons. So here zinc plate is taken as an example of the cathode plate. As you know that the electron was discovered in 1897. Here you can see the number 2 was about to the uh, when radiation stop, current also stop. When radiation fall, then current starts to flow into the circuit. Now there is a threshold value of the frequency at which basically the electron emits from the material surface, and it is different for different material. Right, if you consider the ultraviolet light and visible light, these two light are different. When it falls on these material surfaces, electron emits. Right, so in case of ultraviolet light, the zinc, cadmium, the magnesium, or the material from which the electron emits from the surfaces of the electron, from the surfaces of the material, electron emits. Here, in case of when visible light falls on the lithium surfaces, sodium surfaces, or of the potassium or cesium or rubidium, then the electron basically emits. And this process basically shows that the specific frequency is required to eject the electron from the surfaces. That value of the frequency is known as threshold frequency. As such, you know that energy is quantized and defined in terms of the photon, that is equal to h nu, where h is Planck's constant. This is Planck's constant. So if you have to find out the frequency or the energy of a photon or the incident radiation, you can use this formula. We can write it as E is equal to h nu. So this was just a simple historical steps about the photoelectric effect. Into the next section, we will discuss about the experimental study of the photoelectric effect.